Hi everyone, today I'm talking a little bit about other type of dispersion models. I call it dispersion model 2. In the previous lesson we have talked about models that trying to maximize the benefit of facilities but imposing some sort of restriction of distance or adjacency restriction among facilities, such as pairwise restriction or neighborhood restriction. We're moving a little bit to a different approach here. We're going to talk about the p-dispersion, the Maxison, and the Maxi-min model. So let's talk with the p-dispersion. So the objective of the p-dispersion, right, is to maximize the minimum separation distance. So I'm trying to push, right, I'm trying to push these facilities, of course when they are open, subject to the existence of p facilities. So my budget will limit how many facilities I can have. We are going to introduce a few new variables here. I like to point this out. So D is the smallest separation distance between any pair of open facilities. Now, we don't know what D is because we don't know which facilities are actually open, but once they are open, that's what we're going to try to determine. Right, so this is something we will maximize for. We'll talk about this later on. Xi is a decision variable that is equal to 1 if we decide to locate at I, okay? 0 otherwise. Capital N and smaller case n, this is a set and a number of potential sites. M is a very, very large number that you can set up, let's say like a 2 million or maybe 2 billions again. But be careful here because oftentimes this is of course subject to the units that you are using. So if you were using, let's say, inches, well, okay, then you may want a very large number. If you were using kilometers, maybe, you know, the number that doesn't have to be as large. But anyways, so make sure that's big enough. And then Dij is the distance between two potential sites, I and j. Okay. So here, quickly, then our objective function becomes the following here. The first part is we're trying to maximize D. D, again, is that distance between two sites, but we don't really know what it is. We're trying to solve for this. The number of open facilities should be equal to P or less equal to P, depending on what you want to do. I generally take less or equal to P, so we can see if there is redundancy. And then this partial constraint is actually may look a little bit daunting, but it's actually not so much. It allows you to set an upper bound. Okay, so let's take an example where you have two facilities, I and J, that are selected, right? So you have here I, okay, and then you have J here. Both are selected. We don't know, right? We don't know the distance. This is not a neighborhood restriction where we were specifying a minimum separation distance. Here we don't actually know what that distance is going to be. And so if I selected, then xi is equal is equal to 1. If this one is selected, then xj is equal to 1. If that's the case, so if that's equal to 1, 1, this entire thing becomes 0, 0, this entire thing becomes 0. And so the right-hand side here of this equation is Dij, and so you have something like this. D should be less or equal to Dij. And so if you only had those two facilities in the entire system, right, then D would be equal to that, okay, and that would give you the solution. Now remember, we're trying to maximize D, so as the facilities can be located further away, that's of course better. Next, I will talk about the Maxi-min and the Maxi-sum models, okay? So hope this makes sense, and for the students who are taking optimization class, this relates to homework 6. Good luck. Next, I'd like to talk about the Maxi-sum problem. And in a way here, we are going to finally use demand, nodes, and their value there. Our objective, unlike the p-median, which is to minimize the travel distance, we want to maximize the travel distance. So put things as far as possible from existing customers, and then we are also going to weight that by distance. So that could happen when there are facilities that you actually need in your community, but they are very undesirable, and you want to put them as far as possible from existing population. So here, you know, one way to look at it is, you know, consider maybe things like an incinerator, recycling center, this kind of thing. So our objective is to maximize the distance between demand node and nearest facility. Okay, so we introduce parameter the demand here, the distance between I and j, p the number of facilities, xj is equal 1 if we locate at I, 0 otherwise, and y sub ij is equal to 1 if demand at I serviced by j. So same formulation as the p median here. The only difference is in the maximization, where we maximize the distance times the demand. And so in fact, if you think about this just a second, right, if we had here, okay, let's say a population here of maybe 1,000, okay, and we were to locate here, okay, so you can multiply that distance by 1,000. If we were to locate here, you can also multiply that distance by 1,000, but that distance would be much smaller. So you want to make sure that you take that into account. So that it's not very complicated to solve within a GIS, but the issue here again is that every single demand node must be served one way or another. Okay. I'm going to talk a little bit about different models here. One other extension is the maxi-min, where we're not trying to maximize the sum, like you see here's the sum. This will essentially be maximize the minimum distance, okay, from any demand node to a facility that is actually selected, or a set of facilities selected, so that's determined by P. That is more maybe from the equity perspective, not to leave anyone sort of behind. So I won't talk about the maxi-min, but it works essentially the same way, so its mechanism is quite similar. I'm going to talk about a last model here in just a second. Okay, one related method on a dispersion model is something actually I came across in the literature, and I felt it was quite relevant here. It's the DUS technique that was developed by Arbia, who is a statistician from Italy, and it stands for Depending Areal Unit Sequential Technique. Sequence, so things are basically facilities are added in a sequence manner. I think the best way to think about this is the following. So assume that this square here, right, this square box, is totally black. It's pitch dark inside, and you receive a candle. And so the question is, where should you put that candle in order to maximize the amount of visibility within that that particular area? And so in that case, you would probably put the candle right in the middle, right? So that would probably maximize. Now we could assume, you know, maybe that the walls are homogeneous, so maybe they're all white, or maybe they're all black, whatever, but it's not like one is white and then one is blue or something. No, they're all kind of homogeneous. So you would put your candle kind of in the middle here. So actually, yeah, that's fine. Well, let's assume this is the middle. And if I give you a second candle, where would you put it? And you probably would put it as far away as possible from the existing one. Now, of course, you could take into account the level of reflection from the walls, but we're not taking that into account. So you would put it here as far as possible, right? So this would be your second one. And if you could then put the third one, you would probably put it here, right? So that would be your third one. If you receive a fourth one, you'll probably put it here. A fifth one, you would probably put it here, okay? And if you receive a sixth one, and seven, and so on, you're going to start filling the gaps. And that really gets into what I would almost want to call a systematic pattern, right? There's actually other name for this, a kind of funny one is called the Austrian coffee house pattern, where in Austria you have these very large coffee houses with a lot of tables, and people, if it's the first customer, they're going to try to locate sort of maybe in the middle, and then the second one maybe locating far away, and the third one also far away, and then you have this interesting pattern. And the same happens on train, where you don't especially want to sit next to someone else, you want to sit far away, where it's far away. And okay, this is even more true so with the COVID-19 pandemic. But this is sort of a feeling. And so in terms of objective here, right, you're trying to maximize, right, the minimum distance that exists between any two pair of points here, okay, subject to P facilities. Now this is not the official formulation, but this also can be used beyond facilities, like in sampling optimization. This is very relevant. Okay, I think this just some thoughts, you know, about another technique here for dispersion modeling. Thank you.